I haven't gone back too far in history here. There are these sort of events happening all the time. This is Marshall Islands, and it's this year, a couple of months ago. So now this is not a tsunami. There's probably a storm surge involved, but this is a wind-generated oceanic wave. Now, the thing about waves is, after they hit you, usually about 10 to 15 seconds later, there's another one. Right, wave modeling is an absolute requirement for any coastal designs, coastal engineering, but also just coastal management, understanding what extreme waves are going to do to a coastline. So, I collect movies like this because I find it extremely frightening. And if you go and have a look at what's going to happen with a bit of climate change and sea level rise, you're going to have larger waves and will be able to reach the coastline.
Hello, welcome to today's webinar called Making Waves. As we make some waves today, let's welcome our whole audience from around the world. I'm your host, Cray Price, and look at all of you around the world joining us. Some areas around the coast, but some areas inland as well. So without any further ado, let's welcome today's expert, Daniel, Alexandra. Let's have you turn on your cameras and introduce yourselves to us. Daniel and Alexandra are with JB Pacific. Today's webinar is brought to you by JB Pacific as the sponsor today. And let's have Daniel first introduce yourself. So Daniel, just let us know where you're coming to us from today and a little bit about your background.
All right, sure. Thanks, Craig. So my name's Dan Roger. These days, I think I am what we call a principal coastal engineer, currently based in Brisbane, over in Australia. The good thing about Brisbane is, you guys have been over here, we've got really good links into the Asia, Southeast Asia and Pacific region. So most of my time is either dealing with waves and extreme weather and coastal engineering in these tropical areas and looking at cyclones, typhoons, things like that.
Alex, over to you. Let's have an introduction from you as well. Familiar face. We've had you before on some previous webinars. Let us, for those who are new to you, let us know a little bit about your background.
Yeah, thanks, Gray. So I'm Alex Pascal. I'm a senior coastal modeller at JB Pacific, based over the other side of the country, so I'm in Perth. And I do a lot of the coastal modelling through the Asia Pacific. Just moved back over here a year ago. Before that, I was doing a lot of the modelling from the UK. Worked all around the world. But yeah, it's nice being back in Australia and getting to work on tropical cyclones, interesting weather phenomena like that. So, excited to be here.
Excellent. Well, as stated in the title of today's webinar, we will be making some waves today. So our expert presenters who you just met will step through some of the underlying background theory of wave modeling, and we'll also show off some practical tools that can help you as a practitioner do your own simulations. And in that spirit, we've got an upcoming online course, interactive with the expert presenters that you'll see here today. These are 3 sessions where you will interactively get to step through tutorial models, get through the models yourself, and develop wave models for real-world applications. This is coming up next month, 3 weeks in a row, 2 hours per session. You've got a code there, a QR code that you can scan to register now for those sessions. So we're looking forward to those. Daniel, Alex, anything you wanted to say about this course, this upcoming course, before we get into the poll results?
Look, I can start. Now, it's got a funny name, the wave model. It's called SWAN, but I can assure you it is all about waves. It's one of the stock standard models you can get out there. The best thing is it's completely free and open source. So it doesn't matter if you're in government or in a consultancy like myself and Alex, we use SWAN on every job. So what we got in this course is how to download it, how to set one up, and how to run it over the course of 3 weeks. You'll do exactly like what we do, and we'll be giving you a lot of guidance throughout the 3 weeks.
Sounds good. Let's have a look at the poll results. Looks like if we can pull those up, we had all the attendees, and we've got several hundred attendees today who hopefully give us some statistically relevant results here. Let us know then, Alex, maybe over to you to let us know if you see any surprises here. Looks like a lot of people are familiar with hydrodynamic models. And I guess looking at the types of models that everyone's looked at here, we have 20% of the attendees who have are doing wave modeling in SWAN. Any surprises there that you see from these results?
Not really. I mean, it's exciting to see that there's a lot of people who haven't used wave models before. So that's really good because obviously that's the target of these talks. So that's really good. Yeah. And interesting to see that's a 50-50 split between who's done coastal modeling and who hasn't. So yeah, brand new audience. Yeah.
All right. Well, we'll hope to have some content today for everybody. Dan, you can probably go ahead and start sharing your screen already. We'll be turning the time over to you for a presentation. But in the background, Alex is going to be answering all of your technical questions, and we'll come back on periodically and address a few of those. So do use that Q&A button, if you can, in the background to ask the presenters some questions throughout the presentations here, and we'll try to get to those. And we will hit the most upvoted questions first if we do run out of time. So if you see somebody else's question that you'd like to see addressed, go ahead and upvote that, and we will hit that first. So Dan, I can see your screen just fine, so we'll turn the time over to you. We'll go into the background and address some questions there, and we'll be back with you momentarily. Over to you.
Excellent. Well, look, really, really pleased to be here today. Because I think I've alluded to this in the past, but it's always a good talk if we're talking about waves. Look, a lot of my work involves erosion and a lot of things that are caused by waves, and it's a lot of the focus. But at the end of the day, it's waves that are the things doing a lot of the damage around the place. So today, all we're doing is we're going to talk about waves. A little bit on wave modeling. Well, that's where we want to end up because we want to sort of end with, if you want to learn more about the wave, come to the multi-week training course. But what we're going to be doing at the start is understanding why we want to model the coast anyway. Why are waves so important? Now, section 3 here, just called waves, we're just going to talk about waves, what they are, how they're formed, how they change, and why they're of importance to us all. So that's the rough agenda. Now, I love that we've already got some pre-poll questions out there. And I found in our last course, in fact, our last course on the next screen, we had some really, really interesting discussions. So I urge you to keep putting questions and things in the chat because a lot of the time we don't get to talk about waves enough, even though we are coastal engineers. So the first part of our agenda, coastal training. Showing water school has a range of really, really good training out there, but it's lacking a little bit in the coastal world. And there is this stigma, I think, with coastal modeling that it's really, really hard and it's only done by a small amount of people. And the truth is, it's really not. It's just as accessible as flood modeling, hydrodynamic modeling. If you can do any sort of modeling, computer-based modeling, you can do wave modeling. And if you understand your basic principles of hydrology, you can easily go and understand wave dynamics. Look, we don't have in the coastal world a really, really easy principle like all water runs downhill, which is, I don't want to belittle our coastal, our flood engineers here, but all water goes downhill. Flooding, all right, that's all you have to know. In the coastal world, look, our lumps of water, our waves do go up and they go down. So we do have to understand a few more things, but all within reach. So this is why we've come up with this new wave modeling course using SWAN. So SWAN is an acronym. It's called Simulating Waves Near Shore. So simulating waves near shore. It's just that. So it's nothing to do with the birds, of course. It's just a wave. Now we're going to be delivering we decided to split it up. 3 consecutive weeks. We're going to do 2 hours each. First one, probably going to be a little bit more on wave principles with me. The middle course is going to be all about getting your hands on this model, how to run it. And the last week's all about how to display results and understand what you've run. So there'll be a little bit of homework during the course, but really, really accessible. Oh, that's right. We're going to do a case study in Fiji. Why Fiji? Well, it just happens to be where we're doing some current work at the moment. It's as good a place as any. So we're going to be letting everyone that goes on the course develop their own wave model for Fiji. And we're going to be simulating the effects of a tropical cyclone. So that's coming up. It's about a month from now. I've got some dates later. But also want to promote that if you are just interested in coastal resilience and all sorts of coastal modelling, you can always go and have a look at our last free webinar, maybe October last year, September. And that one's really good as well. That's all about different sorts of coastal modelling and physical modelling. So let's move on. Why do we model the coast? Okay. I haven't gone back too far in history here. There are these sort of events happening all the time. This is Marshall Islands, and it's this year, a couple of months ago. So let's have a play of this one. Hopefully it all comes through. Now, this is not a tsunami. There's probably a storm surge involved, but this is a wind-generated oceanic wave. Now, the thing about waves is, after they hit you, usually about 10 to 15 seconds later, there's another one. All right, wave modelling is an absolute requirement for any coastal designs, coastal engineering, but also just coastal management, understanding what extreme waves are going to do to a coastline. So, I collect movies like this because I find it extremely frightening. And if you go and have a look at what's going to happen with a bit of climate change and sea level rise, you're going to have larger waves that will be able to reach the coastline. And that means we may see more of this. So these are my stock standard movies. You may have seen it if you attended our last course. Myself and Alex, we get to travel around the world, undertaking coastal designs, trying to stop waves as they hit the coast. And the first thing that we have to know is, well, how big are the waves as they're approaching the coast? So that's why we're talking today about waves. Now, there wouldn't be an overtopping risk if there was no waves in the area, and if you could stop the waves offshore a bit, of course. Understanding the boundary conditions, how big are the waves as they're approaching coastline, is key to every coastal engineering project. And not just they're fairly long, those waves there. This is what happens if a cyclone passes close to a Pacific island, so Cyclone Pan. Really, really fast winds, causing lots of shorter waves, but they're just as damaging. And I'll get into some of these terms. Okay, so what is a wave? I used to throw this up, and not many people usually get it right. It's a very scientific description, really. Where we got here? A disturbance of water that propagates in time and space. That'll do. It's good. Now, usually the line after that, in all the textbooks, they say waves transmit energy and not mass. So you don't have one bit of water starting at one side of the ocean and that same bit of water traveling to the other. It's all about energy, which we're going to touch on. But, there is mass in a wave. And that's why when they hit something, it goes boom and there's overtopping. So they're a bit of a strange process here. And they really change as they're traveling in deep water in the ocean. And then as they approach the coastline. You've got bathymetry, you've got coastal structures, headlands. All of this is going to change the wave. They can do a few things, as I've listed down the bottom there, which I'll show you in a minute. First of all, so waves. Under that definition I've just said, a blob of water that travels in time and space, there is a lot of different things that can get considered a wave. So your tide is essentially just a big wave. Goes up and down every 12 hours. We get 2 every day, or 2 highs, 2 lows. Tsunamis, of course, seisures, so these things that you see in harbors, groups of waves, technically a wave as well. But the ones we're looking at, really specifically, are these ones in blue. They're essentially the same thing. I'll tell you the difference in a bit. But wind waves and swell waves. So these are the waves that are all the ones that we surf. So I assume everyone here is a surfer. These are the ones we're looking at. So let's have a look. Generation of wind waves. Now, it is all about the wind. If you haven't heard this one before, it might be a little bit amazing. But these wind-generated waves are all wind energy. So you have to think about the ocean a little bit. Or any water body, we've got a bit of tension in there. Your water likes to stick together. It's a little bit sticky. Now, if you get high enough wind speed, and this isn't high, and just a bit of wind blowing on that, you start to see some ripples. And if that wind keeps up, these ripples are going to slowly go and combine into a very regular wave. So they're going to jump through the steps as I've got down below. your small ripples are going to start to line up, and eventually, you're somewhere like the Gold Coast, you're going to have these lines of waves. And on the right, of course, is how we test them in the lab. It's all to do about wind today. So if you're in a windy area, you're probably in a wavy area. And for people like myself, working in the tropics, we look out for either low pressure systems or I guess high pressure systems as well, but low pressure systems and tropical cyclones or typhoons, depending on where you are. These are the things that are going to have a lot of wind around them, and wind blowing over the water surface are going to start the waves. So that's it really, guys. It's the basis of the waves. Now, when waves are going, they're really hard to stop. The whole point of this video. These are rather small waves. Let's say that's half a meter, and suddenly they're going forward and they hit a structure, and these particular waves are then suddenly going 90 degrees. So they've just completely changed ways. They're going to the right now. And so they've got that energy in them. And the point being is when they're going, stopping them is quite hard. And when a wave really breaks, you're seeing this energy that's built up through hundreds of kilometers, all getting released in one area. So you're going to get turbulence, beach erosion, and wave over. So a couple of new terms in here. Well, you know what wind is. Fetch. We'll start with the first wind. So if you have faster and faster wind blowing over a water surface, you're probably going to get larger waves. Now, I think that should sound very logical to everyone because I guess that's what we've brought up to believe. It's big, fast wind equals a big wave. And that's certainly true, of course. But there's a new part to the puzzle here, and this is this word fetch, because the longer, like in terms of time, the wind can blow over a group of waves, they can turn into longer waves. And longer waves do much different things to smaller waves. So the word fetch is what we use to define the distance the wind is blowing over. So hopefully I have a picture in a second. Okay, let's talk about fetch. A 50-meter swimming pool has a 50-meter fetch. That it's the distance the wind could blow. So I know this is a stadium and it does look like it's got a roof, but if they took off the roof and there was wind blowing over the swimming pool, you would say that's got a 50-meter fetch. You can blow stronger and stronger wind on that swimming pool. At the end of the day, you're not going to get a 2-meter wave. The fetch isn't long enough. The wind just doesn't have enough time to really create long waves, or you can very large waves. A little bit to the north of me, this is the the Gulf of Carpentaria, down the middle, center middle. To get a really large wave on let's say the western coast there of the Gulf, the wind is able to blow over a 450 kilometer fetch. So if you had wind conditions sitting in the right area, blowing exactly from east to west, you could get some much longer waves in the swimming pool, probably some larger waves as well. You go up somewhere like the top right on my screen, got the South China Sea there, coming in towards Hong Kong. If the wind was blowing in this direction, it's got about 750 kilometers. So it's a longer fetch. It's got more time to transfer more energy from the wind into the waves. You can get longer waves, and depending on how fast the wind goes, larger waves as well. Now, this is really important because this is an early simulation I've shared before probably. The colors are actually storm surge. But it's irrelevant. This is a wave model of a cyclone or a typhoon coming into Hong Kong. Now, you can see, of course, it's got a curved wind field. Cyclones are rather circle-ish. But the position of the cyclone and the direction of the wind field will really then start to interact with the fetch that's got available. So longer fetches are going to lead to some more nasty conditions. Now, it's not all about modelling. Maybe I shouldn't say this on a course designed to make you all want to become coastal modellers, but we've got these tools in the coastal world called a monograph. Now, a few of you, if you've mucked around with hydraulics before, I remember these from uni when you were trying to figure out hydraulics in pipes. That's where monographs are, I think, made famous. But it's a graphical representation of a relationship or an equation. So it's a visual calculator. Well done me for writing that. Visual calculator. Now, how we use this, and there is a lot of information on this graph. I'll try to make it color. But you can here estimate your wind speed and fetch. And the monograph is going to tell you what the expected wave height is. So how it works is that the wind speed is on the y-axis. So imagine that we had a wind speed of 20 meters per second. What we do is we lift this bottom line up to about 20. Now, we have to know the fetch, of course. So let's say we had a large lake, something with about 10 kilometers across. What we do then is that we go and line up our green line with the x-axis on about that 10 kilometer mark. There is a slightly harder step that we're going to run through in the full course about correcting for wind duration, but it's just it's another correction there. And where these lines intersect, you can go in there and you can actually read in the nomograph how big the waves are going to be. So in this example, we've got about a 1 meter wave given these conditions. You can actually, if you're getting really good at analysing where all the waves are, you can also go and read what the wave period is. And that's all about the length of the wave. So in this example, we can have a 20 meters per second wind blowing over a 10 kilometer fetch. And we're going to have a wave of about 1 meter and 3.5 seconds. So this one, pretty easy. Anyone can Google wave hindcast nomograph and you'll go and find this. They're all freely available, these ones. And we'll touch on how you're going to go and run this. How you could use this in our course as well, because we want to be able to check our model for telling us the right thing. All right. Now, we're going to keep talking about this concept of the length of the wave, because it's not all about height. So if the wind is blowing on it long enough, it's going to turn from the left picture into the center picture. So on the left, we're going to call that small wind waves. They're really small and they're messy. On the right is what we call swell waves. These are longer. I like to say over 12 seconds. So it takes 12 seconds for each wave to pass. It'll have a wave. The length of this wave in deep water will be 200 odd meters. And, again, linked to the fetch. So in Moreton Bay, this is where I live now in Brisbane, I can never get big surfing, waves like the middle picture in Moreton Bay because my fetch is so small. And this wave period, the length of the wave is really, really important. So I'm going to show you this one. I think it was Tom Shan that shared this one around on LinkedIn a while back, a couple of months ago. Now, this is not a big wave. Looking at this, it's half a meter high, but it's a really long wave. It's definitely, it's not a tsunami, a 20-second wave maybe, but long waves have so much more water. The sheer volume of water there, they don't reflect as much. They can overtop a lot more, and it takes a lot more effort to try and stop these longer waves. So the second I saw these videos, I just thought that's a great sort of animation here showing the power of these longer waves. They don't have to be as big. Really, they're really, really interesting. Okay, so a couple of other terms. The top of the wave, we call the crest. The bottom of the wave, we call the trough. There's a few other terms on there as well. Now, the wave height and the amplitude, slightly different. The wave height, technically, between the trough and the crest. But we often use the word amplitude as well, which is half of the wave height, from around the still water level up to the crest. And here I'm always reminded of different lingo in the surfing world. So if you're a British person, an Australian, and an American were sitting around after a surf, and they've all surfed the same waves, they're probably going to say the waves were different heights. And some of them will be saying, I caught a 3-foot wave, and they'll be talking about the amplitude. The other one will be saying, I caught a 3-foot wave, and they'll be talking about the wave height. So watch out if those three people are telling you the wave heights, the surf's a particular condition, might be vastly different to what you're going to paddle out. So what else can waves do? Okay, they can pass through each other and interact and get very big. So looking at here, a few more movies. I love this one. Pretty classic image. over on the west coast of France, near La Rochelle. Now, what's happened here is the wind was acting in a certain direction, creating some waves. It would have been acting on it for a while because they started to get very regular, and the wind changed direction. Those waves, as we pointed out before, once the waves have started, hard to stop. So the original waves kept going. Then the wind from the other direction started making similar waves. And by the time they got to the coast, they were coming at 90-degree angles from each other. And these waves are just going directly through each other. So, there's no real exchange of mass. They're not bouncing off each other. They're just running straight through each other. Interestingly, when they're actually going through each other, their wave heights can combine and they can turn into a wave suddenly twice as big. Now, we might see, here we go. We call this one backwash. That's what when waves go right at the beach, sometimes they can then go back out to sea. We can get these really warped wave conditions. Makes for amazing photography. Shout out to the ocean photographers out there. Adam Duffy is a great one, travels the world taking photos of these sorts of things. I just find it so amazing how these waves have come into this arrangement. This one, let's try and mute that one. Movie from a couple of years ago now. Some claimed some of the biggest wave ever ridden or caught on camera. The thing with surfers is they're always claiming that they've caught the biggest wave, but this one is on camera. So you can see here how big some waves can get. Interestingly, how these waves down in Portugal get this big. It's all about the underwater bathymetry. The waves are coming in and almost bending back on themselves, shoaling up or combining to create this really, really large wave just here. And overtopping, I'll share one more. It's a nice movie, this one. Over in France. Again, just what happens when you've got a bit of a storm surge that raises the water up a little bit, and you've got some big waves that are going straight at the coastal defense. Now, they've got a lot of energy. When they hit the coastal defense, they have to go somewhere. It can be straight up or it can be over the top. So waves, really interesting. I seem to like them. It's my day job. I don't get to talk about waves enough, which is such a shame. So I'm going to stop here. I'm actually going to hand back to Cray for a second. We're going to see if there's been any comments in the chat about waves before we get on to coastal modeling. So I'm just
perfect.
Yeah.
Excellent. Well, thanks for that. I'm getting a little bit of echo there, so maybe if anybody's not speaking, if we can mute out. But thanks for that. There have been quite a few questions coming in. I'm actually going to let Alex answer. Just to give you a preview of what's coming after the rest of Dan's presentation, we will have everybody come back on and we'll do a panel discussion. But in the meantime, I guess there's a couple of terms here that have come up, and I'm just looking at a few of the questions that Alex has already answered. Let's maybe just take one of them briefly, and then we'll table the rest until the panel discussion. I'm talking about when we are modeling these. You showed these things coming from multiple directions. In the model, do we have to model them as single directions, or can we model them multi-directionally? Alex, I think you've answered that in the chat, but those watching the YouTube recording won't be able to see that. So if you could just kind of restate your answer there, just let everyone know what you answered with.
Yeah, certainly. So I said kind of if we're looking at multi-directional waves, if you're looking at kind of wave inputs on your boundary, if you think about multiple waves coming together, they combine to form, if you think, a single spectrum. So with wave models like SWAN, it's a spectral wave model. So we are, instead of just being able to put, a single wave height, wave period direction in there, we can use a spectrum. And we can get that either from observational buoy data. So if you just think about that buoy bobbing up and down, what that records is a spectrum. So we can put that in to allow us to model those kind of multi-directional components. And then a second part of that, because I wasn't quite sure if you also meant really about, within the model itself. So when you have, for example, wave diffraction and refraction from kind of structures similar to kind of the video that Dan showed with that kind of structure, the wave kind of bouncing and refracting off it into the beach. So we can model those as well. We tend to not model those with SWAN, and Dan will kind of go over a little bit more in the next bit of this talk. We use a kind of phase resolving model for that part. So yeah, but Dan will be explaining the types of wave models next.
Perfect. So that's just a midpoint reminder to everybody that this is interactive. You do get a chance to ask your questions and get them answered. Please do have a look through those that have already been asked. And if you see one that interests you, do upvote that, because we may or may not have time to get to all of them. So with that, we'll turn back over to Dan to conclude the presentation, and then we will bring everybody back on to address the questions that have been asked. Thanks.
Great. Okay. As I flick back, I'll just, of course, answer one more. Yes, we've got a really strange term for the speed of a wave. And yes, it's called celerity. I'm not sure where the origins of that one is. But yeah, wave celerity is essentially a wave speed. Okay. I'll just hide that one. Sorry, Craig, just give me a quick thumbs up. You see that one?
Yep, we can see that, but you put it full screen. There it is. All good.
Over to you. Okay, wave models. So all a model is, if you think about it, a model is anything. It's a representation of something. You make a model of me out of clay. That's a model. You can represent a wave through some equations. There's all a spectrum of models. And models are usually designed to answer a very specific question. So this is a slide from our last talk. So go back and have a look at our other webinar on coastal modeling. But there are sand models out there, and mud models, and vegetation models, and overtopping models. And there are wave models. So wave models are what we're going to focus on today. Now, and really, I like, my work is all in coastal extremes, when things go boom and things go wrong. So that's what we're going to be designing this SWAN modeling course around. So even if you drill into and only look at wave models, you find that there is more than one. There's lots and lots and lots. Now, I think you're seeing the pre-poll questions. 50% of users today have used a wave model. Of those 50%, I saw a third of you used Mike, a third used SWAN, and a third used Delft 3D, which technically is just SWAN anyway. But yeah, there are a few different really common wave models that we use. SWAN is the one we're talking about. But I will show you, just so you understand the differences, in a wave group resolving model. This one simulates groups of waves, and I'm going to show you a phase resolving model, which calculates an individual wave. Okay, this wave model. So this is SWAN. This is what we're going to be learning in the upcoming course. Now, it is all text-based. So over on the right-hand side there, you can see a little screen grab of a project that I was doing once. I've got a couple of extra lines in there, but really, a SWAN wave model can be run with maybe 10 lines of text. It's really, really simple. The model's doing all the hard work. It's solving all of the energy balance equations and things. The setup and running of the model, it's not bad. 10 lines of text, hit go. There is an actual button. You have to type in go, and then have a look at the results afterwards. So let's have a look at SWAN. I should have hit go before. Now, the thing about SWAN wave model, or all spectral wave models, is they operate over a large area, and they're trying to estimate how big the waves are getting from the wind. And a basic assumption here is that the waves are generally going in the same direction and they're turning slowly. So you don't use a wave model, a spectral wave model, to really understand what the waves will do at a structure. Different models for that. But spectral wave model is excellent to understand this sea state, the big, the body of water, how big those waves are getting, and if they're coming in, perpendicular to shore or coming from the north or south, and how big they are, and what the period is. So that's SWAN. I'll show you the two other wave models. This one, they do look a little bit better. Yeah, this is an X-Beach model solving for groups of waves. I like this animation. Fella called Ben did it. Did a really, really good job with the transparent water and things. So this one looks really good, but you can see that waves are entering into our model, and those waves were first calculated in SWAN. So we always need our SWAN, our spectral wave model first before you get into this fancy stuff. This one, This is the Mike 21 Business wave model. This is a hard job. This one's up in Scotland. And if anyone Googles the River Carron wave, soliton wave, you can see that these wave groups here were combining into one big surge of water and going up this channel. So we used the business wave model here to try and solve this. And we did an all right job, I think, and a very hard case study. But we're solving individual waves. So this one's solving individual waves. The last one was solving wave groups. And SWAN is, I would say, solving the sea state. How many waves are even there? How big they are. Okay, now there are some benefits of using SWAN or a spectral wave model. Now, what you can see here is just a forecast I grabbed from a few days ago. This is the Bureau of Meteorology, which is our Met service over here in Australia, predicting the wave conditions throughout the Pacific. This one is using a model called WaveWatch 3. It's a spectral wave model. It's all very, very similar to SWAN. You can see here the scale, how big these wave models can go. And this is what we're all about. There's probably a low pressure system hooting past. Where are we there? Nauru and Niue in those areas, probably right now. So the benefits, quite easy to set up. So you might be thinking, how can you learn all about wave modeling in just 3 2-hour sessions? It's because there are some basic principles that they're quite simple. They really are. And we're going to get you setting up a model. It really just takes a couple of hours to set up. And then you should be able to take that model and adapt it and use it in other places as well. Now, when you hit run on a spectral wave model, it runs in the order of a minute or two, maybe up to 10 minutes if you've got a really complex one. So it's a really fast model, which is it's really what you want. You don't want to be waiting hours or days for a model to finish. So you can run this model in a forecasting world where we set these models up in the cloud, and every 15 minutes we just run it, always updating the results. So there are some good benefits of a fast model. Now you can get quite complex with a spectral wave model, or it can be as simple as only having one input, wind. I'm fairly sure, Alex will have to correct me here, we could model that swimming pool example that I had before and just say, what are the waves going to be over that swimming pool if they're 10 meters per second? It can be really simple. It can really take the place of a nomograph. Now, the nomograph is it's a good way to check your results, but it's not solving things like, what about if my bathymetry is going up or down, or my fetch is varying a little bit in different directions. So a model like SWAN is probably one of the simplest ones you can do. And the good news is that if you already know your waves in one spot, you can use SWAN to then transform them to another spot. All right, so the general modeling procedure. Now, number one, whenever we go into an area, we don't know what model we're going to use. We have to talk with our clients on what are you trying to get out of this project. But of course, this scenario is where we've decided we're going to use SWAN for a regional scale assessment. We're going to figure out how big the waves can get in an extreme storm at your coastal location. Number two, so a model doesn't do one calculation like our simple nomograph. It does many, and it does them on a computational grid. So we have to understand, do we want to just have a line along a grid, a 1D model? Do we want a very regular grid in little squares, or do we want to use triangles? Do we want to vary the resolution? And we'll touch on, of course, as well. Bathymetry, I should mention, in addition to wind, we always need some sort of bathymetry. Datums are a constant headache for us, but there are global, freely available bathymetry data sets around. The GEPCO data set is available everywhere. Rather coarse resolution, but Alex is going to show everyone how she's derived some satellite-derived bathymetry, which you can now get in any short area. Boundary conditions. So setting up the model, this is where the user starts to have, it's a bit of an art in it, and understanding what happens at the boundary, something I don't talk about too much, and then how and where the waves are going to transform into the coastline. This is where we need to have some set rules and we'll run through those, of course, because if you put the boundary in a wrong spot with a model, you could actually create this thing called a shadow zone. So here, I'm allowing waves to enter my model from my offshore boundary. We've got them coming in from the northeast, but this area down here is not going to get any wave energy because I've got to put waves down to this boundary. So establishing your boundary, that's where the skill comes in. Model settings. So the default parameters in SWAN, they're all pretty good. I think there's only one that I regularly change, and that, funnily enough, is all to do with, is it a wind wave type spectrum, or is it swell? You can run through that. Calibration. Now, calibration is really just the process of rerunning your model a bunch of times, tweaking some parameters in order to match some sort of observations that you've got. The problem is there really isn't that many wave observations along a coastline. So we'll run through where you can even find these. Wave buoys are great. There's never a wave buoy where you need it. Design runs. What sort of conditions should you run in a model is always important. If you're doing a cyclone study, how big is the cyclone? Is it a category 2, 3, 4, 5? And where's the cyclone coming from? What's the duration of the wind? I think I saw that in the questions before. Finding the duration the wind is going to blow over a fetch is a challenge, because really you have to predict how long a storm is going to sit in that one spot. You could just assume the wind is going to blow on it forever. Probably be an overestimation, but it's an assumption. Why slow-moving cyclones can be very, very dangerous. Because if they sit in the wrong spot and just allow that continuous build-up of wind energy into wave energy, you can get some really dangerous conditions. And processing the results. So we're going to be showing you how to use Blue Canoe. Now, it's a really, really good little bit of software, freely available as we like. Canadian software, actually, and you can Google it now. It's got some funny spelling, but Blue Canoe. And that allows you to view SWAN result files very, very easily. Okay, so this is the course. There are a couple of typos in there. That's me. And yep, so 3 2-hour sessions, how to get the software, download it, use it, run it. And where we focus on Fiji, I'll show you our case study area. So this is the second island of Fiji, Vanuatu, in a place called Savu Bay. Now, this happens to be an area, a region I'm working in at the moment. We've got some imagery data sets lying around, thanks to Alex, converting some satellite stuff. So we thought this is a great little case study here, because it's essentially a really large lake, still connected to the ocean, of course. But what happens if a cyclone passes straight through these two islands? We're going to get this strong wind that's going to be acting directly over that Savu Bay and hitting our beautiful little community over there at Savu. So we'll be showing you how to set up this model. And as I've said, I think you'll be able to adapt this model for many other places, or stay in touch and we'll, of course, tell you how to put some more boundary conditions in there as well. This is actually my second last slide. Let's call it our last slide. Cray or Joel may be able to now explain how to sign up for the rest of the courses. I'm hoping that I've converted you all into wanting to learn more about waves and wave modeling, coastal engineering, which is the goal here, of course. Myself and Alex, we're always available. This is what we do for a living, and we absolutely love it, right, Alex? So what I'll do now is I'll mute my mic, kill my screen, and we'll hand it.
Yeah, thanks for that. So we've put the links in the chat. If you do want to sign up for that, those who watch the YouTube recording later can just look in the YouTube description and get those logon links as well. And as with many things these days, we'll put QR codes up there that you can scan in. We may need to move that Zoom screen out of the way there, but on the recording, we'll make sure that we have the QR code, complete one for you to be able to use your phone and just get right to that link. So thanks for that, Dan. Thanks for the answers in the background to some of those questions, Alex. This is something that, as you mentioned, the Water School has got a lot of flood modeling applications out there available, and even some of the background hydrology and hydraulics principles that you can sign up for on demand and take any of those courses. But in coastal, we've been a bit lacking, and we want to make up for that. And it sounds like we've got some great expertise on board to help teach those courses. And not just these ones, but there are some others as well that you can sign up for those looking into two-flow modeling and that sort of thing. One of the questions, I guess, that I'll throw out there first, and maybe I'll give Alex a chance to take a stab at this one, would be in that interaction zone. So, we talk about flood models and we talk about coastal models. How easy is it to couple those when you're getting a flood that's coming down out some outlet, and then you also have waves or storm surges coming in? What are your recommendations there? Your cautionary tales that you might put out there for those who might want to undertake such a complex problem?
That's great. Yeah, it's a great question there. I guess one thing to emphasize is that no model is perfect, and you really have to pick your models based on what you want the output to be. So if you're interested in kind of combining that interface between flooding, fluvial flooding and coastal flooding, you have to kind of think about what do you want those inputs at your tidal boundary. So if you're looking at kind of surge, then you might want to have, if it's really up quite far up a river, you might want to use a hydrodynamic model to get that. And then you'll get that boundary condition from your hydrodynamic model to put into your, say, two-flow model or things like that. If you're interested in, say, inundation from wave overtopping, which I saw someone's kind of commented on that before, then what we would normally do is you'd use your SWAN model to get your offshore waves during your storm. You'd propagate them into your nearshore component, and then you would use another model such as Eurotop or some sort of neural network to then take that nearshore wave, put your schematized structure in, and then you calculate what your overtopping rate would be, and then you take that overtopping rate and then put that into your two-flow model. So really it's multiple steps, and depending on what you're interested in or what you need to get out, it kind of depends on what model that you want to use. So yeah, it can be difficult, but there are certain standards that we do have.
Yeah, perfect. Dan, I'll give you a chance to kind of go through the questions that came up while you were speaking. Let's have Alex answer maybe one more that has previously been answered already of the most upvoted questions there. I guess, one of the definitions, I'm not sure if we hit, when we're talking about wind-related, fetch-related, wind-driven waves, the definition of storm surge. So I saw that come up in a couple of the comments. Maybe just let everyone know, for these models, how would that be incorporated? Would it have a slope? How would you get storm surge built into these and putting the waves on top? And I guess another term might be run up. We've heard a little bit about run up in some of these comments. Maybe if we could just do a little bit of a basic definition, recognizing that about 50% of the people here have not done any coastal modeling whatsoever. If we could just have a couple of quick, maybe layperson's definitions of those terms, and then over to Daniel after that to address any others that have been put in the comments.
Yeah, certainly. So I guess storm surge you can kind of think about as kind of the change in water level due to the presence of storm. So you've got the waves coming in, and it's kind of piling up the water level on the coast. And these wave models, they do account for it. So if you can use SWAN in a kind of normal grid, and it can calculate your kind of, you can get your storm surge out, your things like wave setup, which we haven't really gone into. Yeah, so there's quite a lot of terms that kind of come into it. But yeah, so we can use those models to do that.
Okay, thanks. And I think in the course we will provide background materials so that anything that sounds like it's going might be over your head if you have not been exposed to this type of modeling before. We'll make sure you have all the background materials and all the definitions available to you to be able to understand the differences between setup and run up and storm surge and wave, the wind fetch, and then the amplitude versus on the wave, and all those things that Dan put in his diagrams. Dan, over to you. I'm just, rather than asking you one of the questions that's out there, I'll let you pick from the group here. We probably are not going to get through all of these. We've got about 10 minutes to go. We'll try to hit as many as we can, but maybe if you want to just pick one out of that mix to address first. Over to you.
Sure, yeah. There is two questions that I wanted to, I think, address. They're about the same. And where a couple of you are interested in waves, I think, coinciding with a flood. Now, I know this is a really, really hard case. A couple of times, we've looked at projects like this, and we've just had to do the best we can. Now, you can add currents, which is water movement into SWAN, and currents are going to affect how the waves then break in the model. But I think it would be very, very hard to include a SWAN model running over the top of a significant flood event as it's coming down. Now, saying that, the SWAN model couples very, very nicely, maybe on to a third question here, with hydrodynamic models. SWAN is, I think, developed by a range of people, but it's really linked with Deltares who make Delft University. That's so SWAN and D-Wave work really, really cleverly in amongst this Delft 3D model. But the very clever people at BMT, I've seen that they couple to flow very easily with SWAN as well. Now, how this then works is you run your hydrodynamic model. So that's got your water going downhill, the flooding happening, and every minute or two, you pause the model, the hydrodynamic model, and then you run a wave model. And then you get the results and you throw that back into the hydrodynamic model, then you let the hydrodynamic model run for a little bit more. Now, it's a complex process, but all in the realm of what we can do. But I'll end it there with saying that's a complex case when you've got river interactions. Now, you saw the animation when I was trying to solve these soliton-type waves running up the River Karen. On that one, I ignored the currents and the flow out. It was a step too far, and that was a hard model.
Yes, keep the models as simple as you can, as simple as makes sense. So sometimes we end up, battling things that are well within uncertainties of the input parameters, and spending a lot of time on things that don't give you a lot more accuracy in the results. Let's have a look back through a couple of other questions there. Then, Alex, back to you. Then let's do the same. Just have you pick of the many questions that are being asked here. Just go ahead and grab the lowest hanging one, the most upvoted one that you can find.
Yeah. Let's see. I think I'll probably answer the question of how much the bathymetry is kind of impacts your waves. That's obviously a great question. Yeah. And so when you're kind of in the open ocean, obviously your waves are kind of free to form as they want, and as they get closer to the shore, that bathymetry will start kind of impacting the waves. If you think about the waves, each particle of kind of water in the wave is kind of rotating, and as you get close to the shore, they start getting kind of more compressed. And then they'll start kind of influencing the waves. So normally we have kind of a rule of thumb. Again, we'll kind of go through all these rules of thumbs for you if you're in the course, but you have kind of something called a breaker parameter. So often it can vary somewhere between 0.5 and 0.7, 0.8. But generally that's kind of the rule of thumb is once you get to kind of within 0.8 of your kind of wave of your water depth, that's kind of like the maximum wave height that can be sustained. So if you've got a wave that's, let's say a water level that's 1 meter high, the largest wave you could possibly have is 0.8 of a meter. And so if you're going to have a wave that's bigger than that coming in, then you're going to start having interaction with that wave, and it'll start breaking. So that's kind of a good rule of thumb.
Sounds good. All right, and have a look at if you want to get some of the background theory of all the engineering videos out there. We've had a few people come on board as guest speakers and guest presenters on our webinars, and some of them have millions of subscribers, and sometimes they'll get a couple million views on their really big videos. The biggest one yet, to go ahead and Google it and find the wave tank demonstration with Dan right there. Last time around, I think we mentioned that when we highlighted it, and we said, if you click on this one, you may well be the 10 millionth viewer, and somewhere in between, we've passed that now. So Dan's got a video out there with 10 million views. Tell us a little bit about the wave tanks, Dan, and maybe on physical modeling. When you come up with something in SWAN, do you ever go calibrating that to either real measured results or physical models, and that will tie back to some of the previous webinars that we might have done. And another one that's coming up, making a plug for that, around September this year, we're going to be doing another one focusing specifically on physical models. So any comments there, Dan, on reality checks through calibrated measurements and on physical models?
Yeah, great question. Physical models have a role. We haven't used any this year. I'm talking about real ones, but every year we're talking with some hydraulics labs about getting a real life estimate of what our models are telling us. So I would say for any project that's going to be supporting the construction of something very, very expensive, a seawall, new building, you should certainly be checking the wave model results by putting it in a physical lab. In fact, on some of these models, you have to click the little disclaimer at the start saying, I'm not using it for detailed design, I'm only using it for concept design. So physical modeling is great, and it really brings out the kids in the professionals that do that as their job. They actually go and they build a section of the bathymetry in a large lab, in a big warehouse, and they can concrete it and make all the shapes. And they get out there and they build little tiny defenses with something a little bit more complicated than Lego, but the same thing is there. And they're running real waves at it and capturing real physics. It's not equations, it's actually real water. So physical modeling is really, really good and very needed for anything expensive. Now, what we've done is we've made a really small physical tank to demonstrate what happens when waves hit structures. It's our, we call it a mini flume, or definitely a demonstration wave tank. We give the plans for free out there. We just, for any STEM-based activities. It was just today that I gave the plans to someone that wants to build one to demonstrate something to do with tidal and wave energy. So they're out there. Keep your eyes open for more small wave tanks at your nearest STEM fair, or get in touch.
Perfect. And just go to the JBA Trust YouTube channel, and there's a tremendous set of resources there for you to see the impacts of some of these physical models and why those might be useful. All right, we're getting toward the end of our time here. Let's see. I guess let's just let you both do closing remarks, and if you want to wrap in a couple of these questions in the meantime, we've got on nearly 20 of them that Alex has already answered. We'll put the text of these, the transcript of these questions and answers out along with the additional information on the YouTube description and on the website, so that everybody who watches this can have a look at those. A few more open ones that we might be able to hit real quickly. But let's just let you both do some closing remarks. Alex first, and then over to Dan to just wrap it up for the day.
Yeah, thanks. Great there. So I guess wave modeling, it can be complex, but really, it is relatively simple to undertake. It's not as complex as it may seem. A lot of it is really based in deciding, where you want to model. What are you trying to model? Is it swell waves? Is it from a cyclone? Are you trying to find waves in a headland? And then really the hardest part is trying to find model data. So it's either observations, your bathymetry. I definitely see there's a lot of comments here about nearshore bathymetry. How do you get that? We certainly do a lot of open source work, so it's either using kind of your global models such as kind of GEBCO bathymetry, or more recently we've been looking at deriving bathymetry from satellites. So it's from Sentinel-2 imagery, where essentially as long as you've got a few data points, for example, from your chart datums, things like that, or if you've got an existing survey, you can kind of use that to train your model to then predict more bathymetry. So then at least you've got something that's slightly higher resolution than say your 30 meters or more. So certainly we'll be touching on that in the training as well.
That's good. Dan, bring it home for us.
Yeah, well, again, just thank you for everyone for listening. And I would always be really interested in hearing that there's a few more coastal modelers out there. Our flood modeling friends get all of the credit these days with the crazy world that we live in right now and raining and flooding. But coastal modeling, as important, technically more people live along the coast, of and just up in the catchment. So it's it's an area of increasing focus in the future. So yeah, jump on our course, learn how to do it, and enter a very interesting career.
Yeah, great. I want to take an optimistic view, but in some ways it may be a bit pessimistic. But for wave modelers, job security, a few more of those dots that we saw on the map that are not near the coast now, 100 years from now, we may have more people in coastal areas that didn't expect it before, or more people moving out of some of those coastal areas. So keep an eye on the climate change, sea level rises and things like that are all going to figure in here. And so we want to make sure that you have all the content, all the background information, the technical information and skills that you need to continue to improve as a water practitioner. We're grateful to be part of this community. Thank you for your input. Have a look here at the scan here if you want to register for some of these courses. And take a look at some of these additional resources that we have in the coastal realm, quite a few that we'll put in the YouTube description for you as well that you can refer to. And we'd love to see you in this course coming up in April. So with that, thank you very much for your attendance. Thanks, Dan and Alex, for your participation and presentations here, your contribution to the technical fields that are very exciting and will get more exciting as we move forward in a warming climate. We'll see you next time with the Australian Water School. Bye-bye.